Hey everybody, we are going to do another video here. This one is going to be on Fermat's little theorem. I want to have one video dedicated to Fermat's little theorem. It's so powerful, so incredible, and let's get into it. So I love referring to this book, Understanding Cryptography. Everyone should try to get it, or the PDF. It's really phenomenal. So page 167. This isn't really that important, but maybe you want to zoom in a little bit just because it's really, this is really powerful, and I really want to hammer some of this home. So basically, remember we're operating in a world of modular arithmetic where we select a modulus, and all the arithmetic we do is based on remainders of that modulus, okay? And if that modulus is prime, like 5 or 7, you can do some really powerful things here with Fermat's little theorem. In the next video, I'm going to talk about Euler's theorem and how it generalizes this concept for moduli that are not prime. But let's just stick with prime moduli, and you'll see it in a textbook as p, always mod p, okay? And when it's not prime, you'll see it as usually mod n. So basically, Fermat's little theorem is very simple, very few words. Let a be an integer and p be a prime, then a to the power of p is congruent to a mod p. Don't work that hard to get this to click, okay? You want to just get used to this idea that a to the power of p is itself, modulo p. I'm going to go through some exercises and I'm going to show you how it works. But I just wanted to go through how the cryptography textbook introduces this. Because if a to the power of p is itself a, then how most people know Fermat's little theorem is this next step, that a to the power of p minus 1 is congruent to 1 mod p. So I've done them in the podcast before where modulus is 5. Any number to the 4th power turns out to be 1. And then this is the very powerful feature that I'm going to show in some exercises going forward. But the way this gets implemented in cryptography is that what you want is A inverse. You have a number modulo a prime, and you want to know what its inverse is. In other words, you want to know what to multiply that number by to get 1. So remember in mod 5, if I have the number 2, I want to multiply that 2 by 3 to get 1. So 3 is the inverse of 2. And it's just, again, using Fermat's little theorem, we just divide by a again. A inverse is a to the negative 1, which is 1 over a. And that's equivalent to a to the p minus 2 mod p. So it's just this progression. So now that I showed you in the book, let's do some math on this. So the first Fermat's, I'm going to write it in really Fermat's little theorem, write it in very 3rd grade handwriting here. Fermat's little theorem. Okay? It's great, I have that all the way up top. So what we had here is this idea that if we have an integer a, any integer, so we say a is an element of the integers. Don't get intimidated by this notation, okay? This z is basically stands for the set of all integers, which is basically every whole number, every negative number, every positive number, and 0. In other words, that every negative and positive number that's whole. So negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, etc. All of that. That's this. It's called the set of integers. So when we say a is an integer, we're just saying a is an element of the set of integers. Okay, and then what we're saying is that p is a prime number. Okay, and what Fermat's little theorem says in many different ways. One way to say it is a to the p is congruent to a mod p. Let's use some real numbers. let's use 5 as my modulus, okay? So if p equals 5, then p minus, right, then a, what we're saying is any number a, mod 5, so really 1, 2, 3, and 4, and 0 are the numbers mod a, but so any of those numbers, let's pick one. Let's pick 3. 3 to the 5th mod a, mod 5 is, well, we're hoping it turns out to be 3, okay? So what is 3 to the 5th? We got 3, 9, 27, 81, and 3 to the 5th is 243. And I can clearly see that when 243 is divided by 5, right, everything divided by 5 divides either into 5 or 0. So 5 will clearly divide into 240 and then leave a remainder of 3, leaving this being 3 mod 5. Okay? Now, the other way we like to talk about Fermat's little theorem is to divide out by a and make this thing congruent to 1. So we can say that this is the same thing as saying a to the p minus 1 is congruent to 1 mod p. So I don't want you to sit with these letters too long, so let's just do this example again. And I'm going to tell you why this is a particularly powerful one to do. Okay, we would say that 3, once again, 3 to the 4th power is 81, and that is congruent to 1 mod 5. Okay, so I hope that's all very clear. And then the question is, why is this really powerful? Why does this matter? Because I can take a number now, I can take 3 to the 1001th power, which is really hard to do in a calculator. You can't. You'll just get overflow, you'll get 99999, you can't do it. But with Fermat's little theorem, I know that 1001 is 250 times 4 plus 1. So I can say that I can say 3 to the 1001th is 3 to the 4th power raised to the 250th. That gives me the 3 to the 1000 because we multiply exponents. And then we multiply that one more time by 3 to get 3 to the 1001th power. So it's 3 to the 1000th power times 3 to the 1st, right? So, okay, so what now? Well, what happens is this 3 to the 4th is 1. That's what Fermat's little theorem tells us. 1 to the 250 is 1, which means this 3 to the 1001 power is 3. Okay. Pretty freaking cool. I can do the same thing. Let me do another example. 3 to the 1023. Okay? That's going to be 3 to the 4th times something. So it's going to be 3 to the 4th to the something that's going to get me to 1020. I'm trying to do this math in my head, but I think it's 255. And then I have 3 cubed left. Okay, so 3 to the 1023 power is 3 to the 1020th, but that's just 1. Okay, greatest thing you can ever do doing math, and the greatest feeling in the world is to be able to just eliminate a massive part of what you're working on. Just hack it off. This equals to 1. It's eliminated. It's irrelevant. So I can take basically 3 to the 1020th power and say that's just 1. and then multiply that by what's left, which is 3 to the third, which is 27, which is in mod 5, 2. Mod 5. Okay? That's the type of stuff I could do with Fermat's little theorem. Okay, so now let me extend this example real quick and say, what if P was 7? Okay? This is a little dangerous because I don't have my calculator with me. So let's see what happens. If I want to, let's stick with 2. And, okay, so it's a little easier, I guess. 2, and now I'm just going to use the form we like. A to the p minus 1. Okay, so I know 2 to the 6th is 1. Okay, 2 to the 6th is congruent to 1 mod 7. But I'm going to just explain that to you. 2 to the 6th is 2, 4, 8, 16, 32, 64. Okay? 64 is 1 more than 63, which we know is a multiple of 7. So definitely 2 to the 6th is 1 mod 7. 1 mod 7, another way of saying that is 1 more than any multiple of 7, right? Because I'm dividing by 7 and my remainder is 1. So 2 to the 6th is definitely 1 mod 7. So what if I ask the same question 2 to the 1001th power? Okay. Now we know in mod 5 that answer would be 2. I'll leave that to you to figure out. If you can't figure it out, hit me up and let me know and I'll walk you through it. Okay, but let's do 2 to the 1001 now in mod 7. Well, that is going to be 2 to the 6th to some power, and I'm trying to do it in my head right now, which is really probably a mistake. 160 gets me to 960. So let me just say to 160, it gets me to 960. And then I need to get another 36. So that's another 6. Okay, so 166 is the number. Man, next time, I'm never going to do a video again without my calculator. Okay, but 2 to the 6th to the 166th is 909, 2 to the 996, and that leaves 2 to the 5th remaining to get to 1001. So what I'm left with is 32, which is 4 mod 7. Cool? I'm going to stop it there.